test input file'ine VI'yi öğrenmenizde yarar var. VI bir editör. VI file ismi, dosya ismi yazıyorsunuz. Sonra editör dosyayı açıyor. Bir boşluk bırakarak dolar işaretinden sonra kontrol opsiyonlarını yazıyorsunuz. Sonra sistem opsiyonlarını yazıyorsunuz. Bu hafızayla alakalı. Sonra stationary point opsiyonları yazılıyor. Basis set, onların hepsini anlatacağım. Seçiliyor. Guess Huckel dedik burada. Huckel'a göre bir guess yaptık. Ondan sonra da geometri veriliyor. Z matrix koordinatlarında veriliyor bu koordinatlar. İsterseniz X, Y, Z kartezyen koordinatları da kullanabilirsiniz. O örneklere de geleceğiz zamanla. Bugünkü örnekte bu self-consistent field type restricted hard fork demiştik. Yani spinler eşleşmişti, açıkta spin kalmamıştı. Bugün unrestricted hard fork diyoruz. Unrestricted hard fork olunca S, büyük S 1'e eşit oluyor. 2S artı 1 eşittir 3 oluyor. Multiplicity 3 oluyor. Run type ne olsun? Bu sefer gradient olsun, optimize olmasın. Örneğimizde de öyle. Ve local functionlar olarak voice'u kullanalım. Bunların hepsini öğreneceksiniz zamanla. Bu bir örnek. Ve ondan sonra system tim'in burada bir hata yapılmış. System tim'in 1 deniliyor. M-words 32 diye bırakırsanız daha çok hafıza olacaktır. Stationary point'a gerek yok artık çünkü optimize yapmıyoruz. Gradient hesaplayacağız. Basis aynı kalsın. STO'yu kullanalım. Huckel de aynı kalsın ve metilen üzerinde yapıyoruz. Ama bu sefer metilen restricted for hard fork değil, unrestricted hard fork. Yani spinler eşleşmemiş durumda. Sonra çıkıyorum. 2 nokta üst üste W, Q. Ünlem işareti write, quit anlamına gelir VI'da. Yaz ve çık diyorum. Yani save ettim dosyayı. Tekrar açıp bakıyorum. Test input'uma. Gerçekten de dosya olduğu gibi yazmış olduklarımla kalmış durumda gördüğünüz gibi. Şimdi çıkıyorum. Sadece çıkmak için de 2 nokta üst üste quit Q deseniz yeterli oluyor. Çıkabiliyorsunuz bu şekilde. Şimdi Games 2 çuba slarma bakalım. Mid-one diyor. Onu short yapmamız gerekecek. Short seçelim hemen bir yerden. Bir saniye. Bunu kopyalıyorum buraya. Copy oluyor. CP copy için oluyor Linux'ta. Ve VI ile slarm dosyamı açıyorum Truba'da. Short var şu anda. Dosyamın adı test 2 olsun. İkinci örnek bu çünkü. Her şeyi olduğu gibi bırakabilirim. Bunları hazırlamıştım zaten. Buraya dosyanın adını yazacağız. Test input oluyor. Escape yapıyorum. Escape'den sonra 2 nokta üst üste WQ yazdı ve çıkıyorum. Şimdi Sbatch ile Games 2'yi run'a sokabilirim. QStat'la kontrol edebilirim. Şu anda R'de gösteriyor. Short olan bu çalışma. Test 2. Ve yürüyor. Bakalım ne kadar yürüyecek. Kısa bir çalışma bu. Şimdi slarm dosyasına bakalım. 43 41 034. Sonuna gidelim. CNV2. Onu seçmeyi unuttuk. Bak ben de hata yaptım. Test in INP'ye gidiyorum. CNV2 simetrisini sevmedi şimdi. Ama kalabilir. Bu örneğimizde de bu şekilde hatta. Unuttuğumuz bir şey var mı? Yok. Local boys. Check symmetry diyor. Tekrar sınav dosyasına gidiyorum. Evet. CNV2 tamam. Error reading variable x diyor. Olmaması gerekirdi. Check column 5. Tamam. O zaman Z matrix'i daha kolay okuyacağı şekilde yazalım. Buraya karbon yazalım. Unique kullanıyorum şu anda. 6.0 atomic unit'i. Ondan sonra hidrojen geliyor. Hidrojen 2 tane hidrojenimiz var. 1.0 altının altına yazayım. Hydrogen 1.0 0.0 0.82 884 0.70 79. Tamam. Bunlara gerek kalmayacak. Z matrix'ten çıktık. Şimdi deneyelim. Hatta space issue'su olmasın diye şuradan örneğimden ben alayım şunu. Tekrar buraya geçireyim. Tamam. Şimdi tekrar espetch ediyorum. Games 2 dosyama. Bakalım bir hata verecek mi? Hayır, şu anda yürüyor gördüğünüz gibi. Değişik koordinatlar var arkadaşlar. Z matrix verebilirsiniz, kartezyen koordinatları kullanabilirsiniz, unique koordinatlar kullanabilirsiniz. Bunlar Games Manual'da da yazıyor, kitaplarda da açıklanıyor. Ve burada da örneklerimizde de zamanla alışacaksınız zaten. Evet, bitti. Terminated normally. Görüyorsunuz Boyce localized orbitalleri hesapladı. Ondan sonra Hessian gradient of the energy'yi hesapladı. Maximum gradient ve root mean square gradient hesapladı. Ve bunu istemiştik zaten. Sadece gradient istemiştik. Spin density'leri de görüyorsunuz. Alfa, beta, aşağı bakan ve yukarı bakan density'ler. Bond order'ı da görüyorsunuz. Bir bağ var hidrojenle karbon arasında. Ve uzaklığı 1.090. Diğerinin de uzaklığı 1.090 angstrom. Ve bir bağ var karbonla hidrojen arasında. Bu şekilde bir output file veriyor. Diyelim ki biz başka bir şey yapmak istiyoruz bugün. Ne yapmak istiyoruz? Restricted open hard tree-fork diyoruz. Yani ne tam restricted ne tam unrestricted. Arada restricted open games'te olan bir opsiyon. Diğer programlarda fazla bulunmayan bir opsiyon. Copy test input diyorum. Test 3 input. EI test 3 input. Burada açıyorsunuz. Kontrolde self-consistent field type'dır. Şimdi restricted open hard tree fork diyorum. Restricted open hard tree fork. Multiplicity s eşittir 1'den 2s artı 1 yine 3 yapıyor. Runtime yine gradient olsun. Coordinate'ler Cartesian olsun. Tamam mı bu sefer? Ve burada da bitiyor. Voice'u yapmamıza gerek yok bu sefer. System inverse 32'de kalsın. G-bases aynı olsun. Self-consistent field, direct self-consistent field default zaten bu ama yine de yazalım. Bunların hepsine gireceğiz zamanla. Direct self-consistent field eşittir true diyorum. Oradan end diyorum. G-bases, STO ve guess hückel'ı bırakıyorum. Yine metilenle devam edelim. Bu sefer unrestricted hard tree fork değil, restricted open hard tree fork hesaplaması yapıyoruz. STO 2G basis setiyle. Şimdi Cartesian koordinatleri yazmanın çeşitli yolları var. Bu küçük bir molekül olduğu için bunu bu şekilde yazabiliriz ama zamanla daha büyük moleküller için organik moleküller olsun, inorganik moleküller ya da biyokim moleküller olsun daha farklı yazılım biçimlerini göstereceğim size. Hydrogen diyorum, ilk atomum. Ondan sonra karbon diyorum, ikinci atomum. Üçüncü atomum yine bir hidrogen. Bunları silebilirim, kafanız karışmasın. Hydrogen için 1.0, karbon için 6.0, hidrogen için yine 1.0 diyoruz. Ondan sonra koordinatları vermeye başlıyoruz. 0.82, 884, 0.70, 79, 0.0. Karbon olduğu gibi kalsın. Yine burada 0.82, 884, 0.70, 79 ve 0.0 olsun. Evet. Yine write ve quit ile çıkıyorum. 2 nokta üst üste yapıyorum. Öncelikle escape yapıyorum. Escape'e bastıktan sonra 2 nokta üst üste, sonra WQ ünlem. Ve GameSlarm dosyamı da düzenlemek zorundayım. Çünkü input file'ımın adı değişti. Bu test 3 oldu şimdi. Yine escape 2 nokta üst üste WQ ünlem işareti çıkıyorum. Espatch ile Games 2'yi Truba'da işleme sokuyorum. Ve bakıyoruz bakalım. 41.040. Burada ne sorun varmış? As being unique, yes. Okay. Aynısını yaptık halbuki. 1.0, 0.82. Tekrar bir bakayım bir hata var mı? Hydrogen, carbon, hydrogen 1.0, 6.0, 1.0.
Hocam
Bir hata.
ikinci hidrojen eksi 0.82 olması gerekmiyor mu?
Evet, aynı koordinatları girmişim heyecanla. Pardon. Eksi 0 nokta. Şimdi tekrar giriyorum. Tekrar gönderiyorum. Çok teşekkürler. QStat'la bakalım. Run'da. VI SLARM 43 41 041. Evet bitti. Şimdi ne yaptık? Yine bir gradient hesaplaması yaptık. Ve maksimum gradient 0.0572 20 534. Root mean square ise 0.027 55 55 48 çıktı. Bunlar gradient of the energy. Yani gradient'in Türkçesini bilmiyorum ben. Gradient ne anlama geliyor bakabilirsiniz sözlükten. Hocam siz biliyor musunuz?
Yok biz genelde gradient kullanıyoruz derste.
The gradient deniliyor değil mi? Gradient oluyor. Elektrostatik momentlerini görüyorsunuz divergence'ından. Spin density'sini görüyorsunuz nukleus'ta. Alfa density ve beta density de verilmiş durumda. Aşağı bakan ve yukarı bakan. Bonded valence, free valence, total valence bunları görüyorsunuz. Ve son derece güzel çıkmış sonuçlar. Ki çok kötü bir base set kullandık. Bond order yine 1'e yakın. Distance yine 1.090. Bunlar doğru sonuçlar. Ve molecular population ve yükünü de hesaplıyor size her atom için. Charge olarak mesela burada. Eğer bu ileride klasik mekanik için force field'ler, kuvvet alan parametreleri geliştirmek istiyorsanız bu yük hesaplamaları çok önemli olacak. Çeşitli metotlar var. En doğrusu natural bond order analysis'e giriyor. Molecular population sadece 2'ye bölüyor. Load-in population da istatistiksel olarak pek iyi bir matematiksel yaklaşım değil. Bu yükleri yine de kullananlar var arkadaşlar. Ve bu şekilde output failinizi görebiliyorsunuz işte. Fock energy burada. Bare H3 energy, electronic energy, kinetic energy, nucleus repulsion, total energy, bütün sistemin enerjisi sarıyla işaretledim ben onu orada. Eksi 37.2778 öyle gidiyor. O sistemin bütün enerjisi oluyor. Bir örnek daha yapalım. Sanırım GVB'ye geçeceğiz şimdi. Yanlış hatırlamıyorsam. Evet. GVB de H3Fock'tan çıkmış olan bir yöntem. Bunların hepsini göreceğiz. Copy diyorum. Test 3 INP to test 4 INP. VI test 4 INP input file. Şimdi self-consistent field type restricted, unrestricted H3Fock ya da restricted open yerine generalized valence bond teorisini kullanacağım. Bırakın kendi karar versin yani. Run type'da gradient hesaplayalım yine. Coordinate'lerde de bu sefer unique coordinate'ler yerine Z matrix'i kullanalım arkadaşlar. Sistem aynı kalsın. Orada yine hata var. Bases aynı kalsın. Self-consistent field'ı şimdi define etmek zorundayız. Number of core orbitals 3 olsun. Metilen olduğu için. N set O 0 olsun. Ve number of pair electrons 1 olsun. Şimdi yine end kullanacağız. Hatalar yapıyorum. Ve bunun adı da restricted HyDRIFOC yerine GBB olsun title'ı. Ve CNV2C2 simetrisi olsun. Şimdi koordinatları daha farklı bir şekilde yazacağız. Bu testleri evde de çözmenizi tavsiye ederim size teker teker başlangıçta. Ondan sonra teoriye geçmenizi ve testlere tekrar geri dönmenizi tavsiye ederim. C1 karbonumuz, H1 birinci hidrojenimiz, H2 ikinci hidrojenimiz. Şimdi C1 arasında RCH kadar bir distance olsun, bir bağ olsun. H2 ile arasında C1 ile arasında olan şey yine RCH kadar olsun. H1 ile arasında da bir açı var değil mi arkadaşlar? Açı da angle HCH olsun. Ent'i çıkarmamız gerekecek buradan. Ent yapmadan önce. RCH eşittir 1.09 olsun. Diyelim ki bunu veriyoruz. Optimize etmiyoruz gerçi ama optimize de edebilirdik. Açısı da HCH 99.0 olsun. Şimdi entimizi de koyabiliriz. Unuttuğum bir şey, hata yaptığım bir şey olursa söyleyin lütfen. Çünkü hiç kolay değil akşamın bu saatinde ders vermek. Bu yorgunlukla hepimizde. Games 2'ye gidiyorum. Test 3 müydü, test 4 müydü bu arkadaşlar hatırlıyor musunuz? Test 4'tü. Test 3 input yerine test 4 input yazıyorum şimdi. Escape'e basıyorum. 2 nokta üst üste. Write, quit. Ünlem işareti. Çıkıyorum. Dispatch ile Games 2 Slarm dosyamı Truba'ya gönderiyorum. QStat'la bakıyorum. Bu biraz daha uzun sürecek. Çünkü Generalized Balance Bond Theory hesaplaması yapıyoruz. Ama küçük bir molekül. O kadar da çok uzun sürmeyecek. Bir hatamız var arkadaşlar. Bakalım hemen ne hatası yapmışız. 43, 41, 0, 42. Out. Yok mu bir hatamız acaba? Yok, kalmamış. Tamam. Beklediğimden daha çabuk bitti. Bayağı hızlı bugün Tuba. Evet. Gradient'ları görüyorsunuz enerjileri. H3 atom başına düşen enerjileri X, Y ve Z eksenlerinde. C1 için 0,000,386. Birinci hidrojen için değerler burada. İkinci hidrojen için değerler burada. Eksi işareti var X'in önünde. Ve gradient'i hesaplamak istemiştik biz zaten bu çalışmada. Yine charge'ları görüyorsunuz, yükleri görüyorsunuz ve popülasyon analizini görüyorsunuz atomik popülasyonlardan. Ve her atomik orbital için Mulliken ve Lodin popülasyonlarını da hesaplıyor. Ve yine enerjimiz, total enerjimiz değişmedi. Aynı kaldı. Eksi 37.256. Bu çok iyi bir sonuç. Bu şekilde Games'te farklı hesaplamalar yapabilirsiniz. Size bir şey daha göstereceğim. Mesela
yabancı öğrenciler var. İngilizceye geçebilirsek iyi olur diye düşünüyorum.
Okay. I would like to show you also one input file that I run usually. That's for optimization using a DFT level of theory, density functional theory, or you can use any other level of theory. But here it is as an example for you. And I used the Dunning triple zeta valence basis set. And I calculated the forces in an analytical fashion. And you can give the coordinates, as you can see, as XYZ coordinates as I gave here. and it has no symmetry, so it is C1, okay? And then you can list the Cartesian coordinates after their atomic units in columns. So this was another example about the coordinates. You can use Z matrix, unique coordinates, or you can use Cartesian coordinates in games. So, okay. So I want to talk about the theory a little bit today again. But before we talk about the theory, let's do another example. We will go into example 5. So this is a CI configurational integration calculation, CI calculation, and it's a minimal basis set containing 55 configurations. 2 CI roots are found, and the gradient of the higher state is then computed. Note that CI gradients have several restrictions, which are further described in the manual in the Lagrange group. Okay. And I calculated the energies beforehand for you, and this is also available on the game's website. I checked that out. It is a nice experiment here if you want to do that at home. So example 5 would be a nice experiment if you want to do that at home. Another thing that I want to show you is when you go to the game's web page, Gordon group. We lost Mark Gordon. So there are tutorials, okay? There's introduction to quantum chemistry, introduction to games, density functional theory, introduction to MCSCF, and etc., etc. And there are different example games jobs here. You can use any of these, and the input as well as the output is given. And you can check the accuracy of your calculations after you perform the calculations by yourself. But if you want to see the publications from this group, you can see that here. And the courses, here is another course set about quantum chemistry, computational chemistry. I used to use these input files when I wanted to start using games, actually. And these tutorials were very helpful when I was a student. So I suggest that you read all this on the game's webpage. And I can send you also the test example files so that you can run these calculations at home, okay? All right. Are there any questions so far? All right. Then we will continue. Hello?
Hello, Professor. I had a question about this language. Actually, I do not know the language, how make means orders, how to define something. Are we going to learn this in this your lectures, or we should learn by ourselves in home?
So when you look at the game's manual, there's the game's manual.
Mm-hmm.
I gave last week a lecture. It took me about 40 minutes to describe you all what each line means. Actually, there is an input description part. You see?
Yeah, you are right.
So when you go to input description part, you see all the names and all the selections of all variables here that we are using. And these are summarized nicely here.
Yeah, okay. Yeah, thank you.
Okay.
Yeah,
And
okay.
another thing that I want to show is when you go to the introduction.
Mhm.
So in the introduction itself, you will see nice information about games, and it introduces the program, but input file checking and all other things like control, execution type, self-consistent field type, run type, etc.
Mhm. Yes.
So this web page is very useful when you go to games documentation. Okay,
Yeah,
and there
okay.
are test examples which I am using.
Mhm.
Okay, for example, we did the CH2 unrestricted hard-tree for geometry optimization, unrestricted hard-tree for gradient calculation, and restricted or open hard-tree for gradient calculation, and the generalized valence bond gradient calculation today. So when you go to these input files, so when you click on, where is it? The examples are here. Okay, I need to go back. Test example files are here. So you can save that on your computer,
Mhm.
and then you can open that. It comes as a tar file, and then, or zip file, I think. I'm not sure which file is used. Then you can open the tar or zip file, and then you can start seeing the test example files when you want to run it on your own computer. Okay?
Okay, evet, thank you, Professor.
So, all right. So we will continue now today with a short lecture on the way of quantum mechanics. This will help you also to understand how we do some calculations with time more and more. So just a second. Trying with computer audio. I'm closing that here. About the way of quantum mechanics, let me open and write everything for you. I want to share my screen first. So let me open a file. Just a second. All right, I can write here. So when we talk about the way of quantum mechanics, okay, can you hear me?
Yes.
Orkun Hocam duyabiliyor
Yes,
musunuz beni? Tamam.
Yes, we can hear.
Yes. Okay. So the way of quantum mechanics. There are several postulates. The first postulate states, postulate 1, for any probability situation, so for any probability situation, of the system, there is a C function. And this function embraces the coordinates and time. okay, information. And it defines with the coordinates and time information, the entire system is defined by the C function. So let me write it here, mistake here. So for a particle, that is defined by Cartesian coordinates, I have then a psi function that is equal to psi x, y, z, and t information. So I have the Cartesian coordinates and time information in my psi function. For two particles, we have to give the coordinates of both particles. We have to give the coordinates of both particles. Then I have a psi function that looks like this. It has the coordinates of the first particle, the coordinates of the second particle, and the time information. Okay? In general, for the coordinates, I can define that instead of x, y, z as qi. And in physics or in chemistry, you can see this function is qit. That means the coordinates and time information is given to you. And that's the system's definition. The model, this model is a wave. Okay, the model is a wave. This information is in no book, I think. I had to write it down as it is. And psi is a wave function. I is the when I have here an I here qi, I defines the quantum state. And the square of C, my square of the wave function, is proportional to probability. C can be complex, and therefore we are much more interested in this definition rather than this definition. So this is of our interest. Why is this of our interest? Because the psi star is the complex part of psi, is the complex part of psi. What does that mean? For I, we can write instead minus I. For any I can write minus I to get the complex part in the same wave function. To obtain my complex version of my wave function. Okay? Don't forget that I is square root of -1. For example, the square of the function the square of the function. X plus IB, when I check this out, it looks like this. I have X plus IB times X plus IB. And when I multiply these, then I have X squared plus 2IBX plus I squared B squared, right? And I squared is equal to -1. Then I can say that I have X squared plus 2IBX minus B squared. So when I multiply the function by itself, I have the same functions here, okay? Same equations here, same complex equations. Then I still have a complex function, or an answer is still a complex function, right? But on the other hand, when I, if we write minus I instead of I, then I can write X plus IB times X minus IB. And this is equal to what? X squared plus B squared. So this is not a complex function anymore. I don't have I in my function anymore. That's why I'm interested in this equation rather than this equation when it comes to my wave function. When we talk about psi star psi d tor property, whereby the particles have a volume of d tor, let's say it's dx, dy, dz, and psi star psi d tor property is proportional to finding that particle in that volume, okay? The particle has to be in one place, right? The particle has to be somewhere. The particle has to be in one place. That's why when I take the integral over all space, then my equation is equal to 1. When this is provided, we say that psi is normalized. Okay. Additionally, our psi has to be finite. Has to be finite. It has to be, it has to have one value. And it has to be, in English, it's continuous. Such a psi is a good behaving psi. Why? So when I have such a wave function, then I have a good behaving wave function. Why? Any answers? Why do I need a finite, one value, and continuous wave function? So let me give the answer because none is coming from you. It has to be finite because the probability 1 means something. Okay, the probability 1 means something. What does that mean? So a probability of 0 would mean that the event is not happening, is not taking place. Therefore, probability changes between 0 and 1, like a particle in one box, in one-dimensional box. Its probability at a given place, at a given coordinate, is changing between 0 and 1, right? Probability changes between 0 and 1. If psi is infinite, if I had a wave function that is infinite, what would that mean? It would mean that the probability could be greater than what? I'm listening.
1.
Yes, probability could be greater than 1. Sehr schön. Probability could be greater than 1. Why does my wave function have to have one value? Well, there's only one possibility for the particle to be in a specific region, right? There is only one possibility. For the particle to be in some region. Of the space. Similarly, hydrogen atom electron has one probability at a certain distance from the nucleus. At a certain distance from nucleus, there cannot be two different probabilities. So hydrogen atom electron has one probability at a certain distance from nucleus. So that's why our psi functions have one values. So why does it have to be a continuous wave function? Continuous. So if the electron has a specific probability at a certain distance from nucleus, then the probability of finding that electron at a slightly different location changes from its initial state in a very small amount. So the probability function cannot be incontinuous. Meaning what? So if I change the location of the electron, let's say I have an electron and I change its location, change by 0.000000001%, then probability cannot be twice, let's say, or 3 times or 4 times, let's say twice as bigger as its initial state. Okay, so if I have 2 functions and the integration, let's say I have these functions, gives me a 0 over all space, or I can have this, gives 0. Then I can say that these functions are orthogonal. Okay. So what is the wave function when we go deeper into it? The wave function in 1924, de Broglie, showed that a particle that is moving has a wave character, okay? A particle that is moving has a wave character. This was proven by experiments in 1927, proven by experiments. Schrödinger applied the wave model on a hydrogen atom. Okay. In these, the model had to be created for a three-dimensional model. In classical physics, this three-dimensional can be defined as when I have this function and I have dx squared, this function, y squared, my function is v squared is equal to wave's phase velocity times the second derivative of the function based on time. For an harmonic motion, like a sinus wave, this could mean with the frequency that I have minus 4p squared frequency square in the function. From de Broglie, we know that lambda is equal to h divided by n mu, and this is equal to m squared mu h squared. H is the Planck's constant here. When we write this in, so when I write this in this equation, then I can have del square second derivative dt square is equal to what? Minus 4p square m square u to the fourth h square and my function. When we put this into the classical function, so when I put it into a classical function, then we can have del square c, or my function epsilon square z squared, if I could write, minus 4p squared m squared mu fourth h squared times my function. So when I say that E is the total energy, T is my kinetic energy, and V is my potential energy, then I can say my kinetic energy is equal to my total energy minus the potential energy, which is equal to what? Minus 1 divided by 2 m. Yes? Are you following? What do I have to write here? Right? You're familiar with this equation.
So I can rearrange this entire equation into which is equal to minus 4p squared m squared divided by 8 squared 2 times e minus v divided by m times my function. A reordering of this three-dimensional wave would give me what? Del x squared plus del y squared plus based on del z squared plus 8p square m divided by 8 square e minus v times my function is equal to 0. So this is starting with a classical equation and coming to this point. We have derived the time-independent Schrödinger equation. If we rearrange that, then I can write h bar to square divided by 2m and h bar is equal to h divided by 2p. So this is my Laplacian. And so time-dependent Schrödinger equation, this is the time-independent Schrödinger equation. Time-dependent Schrödinger equation would look a little bit different. It would be based on, again, Planck's constant divided by 2p divided by 2m, my Laplacian, my wave function, potential energy. So this would be the time-dependent Schrödinger equation. And this can be written, as you all know, in this equation. This one is the Hamiltonian operator. And the Hamiltonian operator can be defined as by 2m del squared del x squared plus del squared del y squared plus del squared del z squared second derivatives plus my potential energy with the xyz coordinates. And the total energy is equal to this. And the total energy operator from here on would be equal to the all-known, well-known equation that looks like this. So some equations that are mostly used in quantum mechanics before we continue with all this are, so when we go to some equations that are mostly used in quantum mechanics, we can write the coordinates. The coordinates in classical term are given as x, y, z, and r, right? In QM, in quantum mechanics, it looks like this. Momentum in classical terms is given as px, py, pz. In quantum, it looks like this. For Px, Py, and Pz. And when I write about the kinetic energy, then I have P squared divided by 2m, and it would be equal to del x squared, del squared, del y squared, plus del squared, del z squared. And energy, which is, let's say, E in classical terms, is IH del divided by del T in quantum mechanics. Potential energy, which is just V in classical mechanics, becomes this in quantum mechanics. And then we can write angular momentum in Cartesian and polar coordinates as well, but I'm not going into that today. So, and then we have operators in quantum mechanics, and most of the students are lacking with the basic mathematics of these equations. So I'm going to provide them today. So linear operator, what is a linear operator? If a operator,
Aras'cığım,
yes? Hello? Okay. If an A operator and f1x and f2x are the functions, and C1 and C2 are constants, then I can write the A operator based on my constant times my function plus the second function, and it would look like this. If this is the case, if it has this form, then it's called a linear operator. For instance, let's consider the first derivative. If I have such a linear operator and I write it down like this, then I have C1 d divided by dx f1x plus C2 d divided by dx f2x. So this is the first derivative is a linear operator. But if we take the square, for example, if we take the square, so let's say I have my A operator, C1 f1x, and this shall be equal to C1 f1x plus C2 f2x square to the 2, so square. So when I write it down, then I have, when I open it here, I have this function with my operators, which is equal to C1 square f1 x square plus C2 square f2 x square plus 2 times C1, C2, F1x, F2x. So as you can see here, this is not equal to C1 F1 x square plus C2 F2 x square. So what can I say? I can say it's not linear. It's not linear. Okay. When it comes to addition and subtraction of these operators, then I can state I have my A operator plus minus B operator times my function. This is equal to A operator times my function plus minus B operator times my function. It can be replaced, so it means A plus B is equal to B plus A. And A plus B plus C is equal to A plus B plus C. So when this is the case, we call it associative. Okay. When it comes to multiplication, so let's say we have the operators A and B times fx, then I can write it as this in this form. It's also associative. Why? Because I can state that A operator times B operator plus C operator fx is equal to A operator, B operator plus A operator, C operator fx. So commutator is defined as in quantum mechanics. What is a commutator? So I can have the A and B operators, then the difference between these two gives me the commutator. When it comes to commutator properties, I can say that A, B is equal to A, B minus B, A, which is equal to minus B, A, minus A, B, right? And this is equal to minus B and A. So this is one property. The second property is when I have the A operator, C times B operator, then I can say that this is written as this with the commutator as it should be. And this is equal to A operator, B operator minus B operator, A operator. This is then equal to say C, A, B operator. And then I can have three of them. If I have A operator, B operator, and C operator, I can have, let's say, A operator, B operator, C operator. Then the commutator is what? A, B, C minus B, C, A, right? Which is equal to A, B, C minus BAC plus BAC minus BCA. So this is equal then to ABC plus BAC. So there are different commutator properties that you can look up in your books. And then there's the, after linear operators, there's the Hermitian operator that is very important in quantum chemistry and quantum mechanics. And we will talk about the Hermitian operator next week, actually, because it's too much information already for today for those who are starting new, because we have undergraduate students as well in this workshop. So what else do I want to say today? So let me get into something that I prepared, actually. And it's an overview of computational quantum chemistry. So when it comes to the definition of computational chemistry, we use, let's make it larger. We use mathematical approximations and computer programs to obtain, yes?
Before we start, can we take a break to get coffee or something for 5 minutes?
Yes, it would be very good for me too. Okay, thank you. Thank you. Let's wait a little bit more. Actually, maybe they are still in the break. And quantum chemistry. Computational chemistry is a rapidly growing field in chemistry. Computers are getting faster and quantum computers are coming up now. It will be much more fascinating from now on. Algorithms and programs are maturing, and there are also quantum computing algorithms that has nothing to do with quantum mechanics, okay? But it's interesting to see the algorithms developing, and we are active in that area too right now. So some of the almost limitless properties that can be calculated with computational chemistry are equilibrium and transition state structures, dipole and quadrupole moments and polarizibilities, vibrational frequencies, IR and Raman spectra, NMR spectra, electronic excitations and UV spectra, reaction rates and cross sections, and thermochemical data. So the motivation of quantum chemistry is the Schrödinger equation that we just derived, and you understood that Schrödinger equation, time independent and time dependent, can only be solved exactly for simple systems like a hydrogen atom, or rigid rotor, or harmonic oscillator, or for a particle in a box. For more complex systems that have many electron atoms and molecules, we need to make some simplifying assumptions and approximations and solve it numerically, the Schrödinger equation. So all these assumptions and approximations, almost all of them got the Nobel Prize actually. However, it is still possible to get very accurate results even though we have these assumptions and approximations, but you can get also very crummy results. In general, the cost of the calculation increases with the accuracy of the calculation and the size of the system of interest. So when we get into the theory, 3 parts to solving the Schrödinger equation for molecules are first the Born-Oppenheimer approximation. This leads to the idea of a potential energy surface, the expansion of the many electron wave function in terms of Slater determinants often called the method, and representation of Slater determinants by molecular orbitals, which are linear combinations of atomic-like orbital functions, which is the basis set. So when it comes to Born-Oppenheimer approximation, what is it actually? So we have the time-independent Schrödinger equation here. We will be solving the time-independent Schrödinger equation. And this is for many electron and atoms and molecules. We just saw these equations just before the break. And last week I showed this equation, the Hamiltonian operator. So it has the nuclei kinetic energy, electron kinetic energy term, which is my kinetic energy, the nuclear repulsion, nuclear electron attraction, and electron repulsion terms, which is the second term. And you know by now that what these equations are, I just derived them. So in the Born-Oppenheimer approximation, since we cannot solve the Schrödinger equation exactly for many electron molecules, the wave function of the many electron molecule is a function of electron and nuclear coordinates, okay? The large capital R is the nuclear coordinates and R is the electron coordinates. The motions of the electrons and nuclei are coupled. However, the nuclei are much heavier than the electrons, right? It's about 2,000 times more heavier than the electron. So, and consequently, nuclei move much more slowly than do electrons. To the electrons, the nuclei appear fixed based on the Born-Oppenheimer approximation. So to a high degree of accuracy, we can separate based on this approximation, electron and nuclear motion. So the electronic Schrödinger equation, now we can solve the electronic part of the Schrödinger equation separately, all right? So it looks like this. Oops. It looks like this. And we have the coordinates still as the function of the coordinates. And the Laplacian is here again. And the Born-Oppenheimer approximation leads to the idea at the end of a potential energy surface. So this is, for example, an example of HGBR. And here's the potential energy surface with the distance between these two atoms. And this is what we got from Born-Oppenheimer approximation. So the nuclear Schrödinger equation, once we have the potential energy surface, we can solve the nuclear Schrödinger equation. And solution of the nuclear Schrödinger equation allows us to determine a large variety of molecular properties, such as the vibrational energy levels and IR spectra from there on, or thermochemical properties from there on. So for a polyatomic potential energy surface, this is an example here from some calculations with oxygen and hydrochloric acid. That gives hydroxide and chlor in the system. And this is how the potential energy surface of this reaction looks like, okay? Using the Born-Oppenheimer approximation. So what is the method in quantum chemistry? How do we solve the electronic Schrödinger equation? For systems involving more than one electron, still isn't possible to solve it exactly because of the last term, the electron-electron interaction is the culprit, as we know from last week. And approximating the psi, the wave function, is the method. After the Born-Oppenheimer approximation, the next important approximation is the expansion of the wave function in a basis of Slater determinants. So I spoke about the Slater determinant last week too. And this is how we described the Slater determinants last week. And we talked about the Hartree-Fock approximation for almost an hour. So the Hartree-Fock approximation is a method in quantum chemistry. And it uses the Slater determinants as configurations. An example is neon. The ground state configuration is 1s2, 2s2, 2p6. This would be my function, or it might be 1s2, 2s2, 2p5, 3s1. It has the same electron number. If you had a complete set of functions, the expansion would be exact, not feasible, okay? The exchange is exact. Hartree-Fock approximation uses one determinant, and this is a variational method. Energy for approximate wave function will always be higher than the energy of the true wave function. Uses self-consistent field procedure, finds the optimal set of molecular orbitals. Each electron only sees average repulsion of the remaining electrons. No instantaneous interactions are appearing in Hartree-Fock approximation. So when it comes to the accuracy of Hartree-Fock calculations, which we did on games too, with restricted Hartree-Fock, unrestricted Hartree-Fock, restricted open Hartree-Fock, we did all these calculations in games as test examples for methylene, for example, and the values were in accord with experimental values. But with more electrons, the Hartree-Fock wave function typically gets worse. And fortunately for the Hartree-Fock method and all quantum chemists, chemistry is primarily interested in energy differences, not total energies. Hartree-Fock calculations usually provide at least qualitative accuracy in this respect. So even though the total energies are not correct, the trends are correct. Bond lengths, bond angles, vibrational force constants, thermochemistry can generally be predicted qualitatively with Hartree-Fock theory. And here you see how it agrees with the experiments for carbon monoxide. Okay, the error can be bigger for carbon monoxide than for a smaller atom. And when it comes to electron correlation, well, the electron correlation is a problem in Hartree-Fock because the difference between energy calculated with exact wave function and energy from using Hartree-Fock wave function is the electron correlation, okay? It accounts for the neglect of instantaneous electron-electron interactions of Hartree-Fock methods. In general, we get correlation energy by adding additional Slater determinants to our expansion of wave function. So Hartree-Fock wave function is often used as our starting point. Additional Slater determinants are often called excited, and different correlation methods differ in how they choose to include and calculate the coefficients. So here you see an example for excited Slater determinants for Hartree-Fock type, S-type, D-type, T-type, and Q-type. And when it comes to configuration interaction, which is another method, we will talk about it actually more next week. We will do the configuration interaction example next week. And then we will talk about the configuration interaction methods more. What I ask you to do is please read the Introduction to Quantum Chemistry and the Computational Chemistry book along with our practices. And the games webpage is very, very important. Look at the tutorials there and look at the manual and